The point of a factory-like game is to process resources. Last time we took a look at the machines that actually do the work, like the drill, the furnace, and the assembler. But for those machines to really work as a unit, they need power. And more importantly, they need to share it. In this game, machines are connected using cables, and each machine has its own internal battery, but once connected, all those batteries combine their capacities, essentially forming one large battery. So instead of thinking about individual machines, we start thinking in terms of networks. But the challenge is figuring out which machines belong to which network, especially when players can freely add and remove machines and cables at any time. The first naive approach is storing networks in simple arrays. This seems fine for 5 machines, but it's a performance trap. Every time a machine asks, "Who am I connected to?" the game has to scan every single array and every single machine within them. If you double your factory size, you quadruple the work, so it's not ideal. Another approach is to give each machine a list of directly connected neighbors. Storing direct neighbors is even more dangerous. To check a connection across the map, the computer has to walk the path. It visits neighbor after neighbor in a recursive loop. Another, much more effective approach is to use a data structure called union find. In union find, every machine and every cable is treated as a node. Each node stores a reference to a parent node, and by following those parent links, we can figure out which network it belongs to. At the very beginning, every node starts off as its own parent, meaning every node is the root of its own tiny network. As machines and cables are placed, we start merging these tiny networks together using union operations. Union operations gradually build networks into shallow trees, keeping most nodes pointing directly to the root. This happens thanks to a simple rank system, which always attaches smaller trees under larger ones, preventing long chains. After placing machines and cables, the internal union find structure might look something like this. Machines and cables are both nodes, and they all participate in the same structure. It's important to note that this tree is symbolic. It does not represent the physical layout or wiring of the factory. It only represents connectivity, which nodes belong to the same network. To check whether 2 machines are connected, we don't traverse the network. We simply find the roots. If both nodes point to the same root, they belong to the same network. For example, G and H both resolve to the same root, so they are connected, even though they are linked through cables. Now, if we want to connect 2 entire networks together, this operation is incredibly cheap. All we have to do is make the root of one network point to the root of the other. That's it. Network 2 is now part of Network 1, and connectivity checks remain just as fast. We are still only comparing roots. Union find is great at joining, but bad at splitting. When a cable is removed, the game has to force all nodes in that specific network to rebuild their connections from scratch. But even with that extra step, the benefits of union find far outweigh the costs. With the network established, distributing energy becomes a simple loop. Every frame the generator identifies the nodes in its network that still have capacity and fills them one by one. It calculates how much room is left in a machine's battery, tops it off, and subtracts that from the total produced. Another problem I had to solve was the orientation of cables, because they shouldn't just work correctly, they should also look correct. When a player places or removes a cable, the visuals need to update instantly so the wiring makes sense. For each cable that was either placed or removed, the game looks at the cables directly next to it. With the cable's position and the positions of its neighbors, it can determine how it should look. So depending on its neighbors, it can either be a straight line, a T-junction, a corner, or a full cross. Once the game figures out the orientation, it can simply pick the correct texture and apply it to the cable sprite. Whenever a machine or a cable enters or leaves the scene, they trigger a refresh that rebuilds that union find structure we just looked at. It also updates any nearby cable orientations, ensuring that visuals and the logic always stay in sync. This is thanks to these two signals that listen to nodes entering or leaving the scene. Multiple objects can exist on the same tile, stacked on top of each other. When that happens, a small UI list appears in the bottom left of the screen, letting you scroll through them using mouse wheel, touchpad gestures, or keyboard shortcuts. As you scroll, only the currently selected object stays fully visible while the others fade out. This makes it much easier to focus on exactly what you want to interact with, especially when laying down cables. Behind the scenes, the UI reorders the stack and updates highlights in real time, so interactors always apply to the topmost focused object. Every canvas item in Godot exposes a modulate property, which lets you tint or fade an object by adjusting its color and alpha. This means that I can make non-selected objects semi-transparent without writing any custom shaders. There is also a toggle in the top right corner of the screen that lets you focus on the wiring itself. When you activate it, every object except wires becomes semi-transparent, using the same canvas item modulate trick. This makes it much easier to see how cables are connected across the map without any extra clutter getting in the way. And that's how machines share energy in industrial dungeons, from individual batteries to fully connected networks. In the next video, we will take a look at pipes and how they transfer items between inventories. Thanks for watching.